good afternoon. So I thank the organizers for inviting me and having me to talk about my recent work. So it's always good to be back at QMAT. So today I'll be telling the story about the quantum Griffith singularity observed in off-stoichiometric granular thin films of niobium tin. So this is a very recent work which we have done. So let me see how we can go through it. So since we'll be talking about quantum Griffith singularity, so before understanding this in this superconducting system, let me show you what is known about the quantum phase transitions in superconductors. So about quantum phase transitions in superconductors, the prototype of that is a superconductor insulator or a superconductor metal transition, which is well known since a very, very long time, which is driven by quantum fluctuations, and they can be triggered by any external parameter like the film thickness. This is what is a result shown in amorphous bismuth film. It's a very old result in 1989, where by tuning the film thickness, you can go from a superconductor to an insulating phase. Similar results seen by changing the doping concentration. This is in MgB2, where again you can drive a superconductor to an insulating phase. This is with tuning the electric field, and this is with tuning the magnetic field. With different systems, the result is the same. You are going from a superconductor to an insulating phase. So mostly seen in two-dimensional disordered thin films and Josephson junction arrays. So how is this SIT understood in these kind of systems? So you know, for students who don't know, that superconductors are governed by an amplitude as well as phase. So this understanding the SIT is actually being understood by two competing models. The first one is basically a amplitude dominated scenario, where it is assumed that you go from a superconductor to a Fermi insulator phase, and the transition is mainly driven by the breaking of the Cooper pairs. So there were measurements which were actually done in this insulating phase of this superconductor to insulator transition, so in this phase, and it was observed that the superconducting energy gap closes in this scenario. However, there is this alternative scenario where you go from superconductor to a Bose insulator phase, mostly seen in inhomogeneous and granular system, and this is the phase dominated scenario. Here the transition is mainly driven by the localization of the Cooper pairs, and here what you see is again what I said is superconductor to the insulator transition. But if you actually measure the superconducting energy gap in these insulating samples, you would actually see the gap. That means the gap persists in the insulating phase. So this is the understanding of the SIT. Of course, there are controversies. It's still controversial as to know which one actually follows the Fermi insulator scenario on the other, the Bose insulator scenario. Okay, so when you come to homogeneous superconductors, what are the experimental signatures for a conventional quantum phase transition? So this is an experiment which was done in gated two-dimensional semiconductor superconductor array. And here you can see that by tuning the gate voltage, you can go from the superconductor to the insulating transition. Now, if you look at the magnetoresistance isotherms, you see that they all cross at a single point. So this is this quantum critical point where the system is going from the disordered to the ordered to the disordered phase. So this is the classic experimental signature of a quantum phase transition in which is actually known in these systems. So this was electric field tuned, and since I will be showing a lot about magnetic field tuned systems, so this is a similar results where you see these magnetoresistance isotherms, where also you see the single crossing point, that is the single quantum critical point in these kind of SIT driven systems. So how do you look at how does the phase diagram look like? You see this ordered to disordered phase transition driven by this parameter PC, and you have this quantum critical point. In the quantum critical regime, you have the physical properties follow the standard power law scaling, where the relaxation times diverges with shows the power law behavior. Now, if you go to different kind of systems where superconductors have quenched disorders. So previously those were systems where you were more or less homogeneous. So now if you go to, this is a result in granular titanium nitride thin film. So again, when you, this is a magnetic field tuned superconductor to insulator transition. So, you change the magnetic field and you go from a superconductor to the insulator transition. But now if you look at this magnetoresistance isotherms, you see very different behavior than what I showed you before in the previous slide. Here you just do not have a single crossing point. So, for different temperatures, the crossing points, there are multiple number of crossing points, and this actually is the classic signature of a quantum-Griffiths singularity or the quantum-Griffiths phase which is formed. So, this is the phase which is formed over here, and this is what we will be looking at. So, how do we understand this phase? So, in superconductors with quenched disorder, what you actually form is some rare spatially extended regions which are ordered, and these rare regions are ones which show extremely slow dynamics, and these are the ones which start controlling your physics. So, the main result or which the smoking gun proof of a quantum Griffiths phase is that it will show the physical properties will all show activated scaling. So, if you look at the dynamic critical exponent, you will start seeing divergence close to this quantum critical point, and this is what is the classic signature of the quantum Griffiths phase. So, what we did is that we were trying to probe this in a system of niobium tin. This is a very old known superconductor, and you might think that why we are studying this. Of course, this has been studied mainly for technologically relevant quantities, and we do thin films. So, we will be growing thin films. So, if you look at the variation which is known, the variation of the superconducting transition temperature in these systems. So, as you change the thickness, so this is the x-axis is thickness and Tc. So, the Tc is known to decrease with the thickness. Now, what our question was that can we tune disorder in these kind of systems to get a quantum phase transition? So, with this we actually made two kinds of niobium tin thin films, one which is of course the stoichiometric ones, and the one which is slightly off stoichiometric, which is a bit of tin rich. So, we had 72 to 28% of tin. And of course, we see that more or less it you get similar phase transit, similar XRD patterns in both of them. Now, important thing to note is that these there is a bit of peak broadening in the XRD which we observe as we decrease the thickness of the films, and that tells you that these films which are forming are basically granular in nature, where the grains are extremely small in size. So, we have another important thing to worry about, which is the particle size in these systems. So, if you look at the microstructure of this, so first let us look at how the niobium 3 tin films behave. So, you can see this is the microstructure for an 18 nanometer film. So, you can see very small grains, of course, they form clusters like this. So, it is and the grain size decreases as you decrease the film thickness, a result which we also saw from the XRD. And basically the grain boundary thickness is what increases as you go down in thickness. Of course, we also did some more characterization using TM to see really we get these small grains in a 10 nanometer thing, and of course, the phase is retained up to the lowest thickness possible. Now, when we grow these niobium 2.5 films, this of course shows a similar microstructure as the niobium tin films, but to really see the granular microstructure, go to very low thicknesses of about 9 nanometer, and what we notice that when we reduce thickness by very small amounts, you see that of course the average grain size is given here, you have small grain sizes, but you also get a grain size distribution which is obviously known. So, granularity increases with decreasing film thickness, and this will have some bearing on what I will show you later on our results. Okay. So, first when we grow the films, we have to of course characterize the superconducting properties. So, first we satisfied ourselves that when you grow niobium tin on substrates which are niobium also, which is important for the radio frequency, superconducting radio frequency resonators which are used for accelerators. So, you see that we get 18 Kelvin Tc. Now, the main result is over here. When we decrease the thickness, we see a decrease in the superconducting transition temperature, and it is for both the series we see almost the similar trend. However, the Tc decreases faster for niobium tin films, niobium 2.5 tin films below the 50 nanometer thickness. So, this is what we wanted to study, whether we wanted to see whether we can see an SIT in this system. So, we looked at we plotted the square of the resistance or the sheet resistance versus the temperature plotted in the log scale for films of different thicknesses. And what we noticed for the stoichiometric films, we go from the superconductor to, of course, when we cross the quantum resistance, we see an insulating phase, but it starts dropping down beyond, we could not measure lower to 1 Kelvin. So, of course, we can see that there is some downward trend over here. However, for the niobium 2.5 tin system, what we noticed is that you see this superconductor to insulating phase, and this is happening at a much higher thickness of around 13 nanometers. So, below 13 nanometer itself, we start seeing superconductor to insulator transitions. So, which tells you that the off stoichiometric films is of course more disordered, but we need to understand it or quantify it better to be able to corroborate our assumption. So, how do you measure the disorder in these films? So, it is well known that this parameter KFL is a measure of the disorder strength. It is usually taken as the measure of the disorder strength in the community. So, you can measure this by doing Hall measurements, and that is what we did, and this is KFL as a function of Tc, and you see that the KFL decreases, and for our thinnest film we actually go to KFL values which are even less than 1. So, for people who might be knowing that KFL 1 approaching 1 gives to the very strong disorder regime, and so we conclude that we are actually entering a very strong disorder regime in these systems. So, if you want to understand the variation of Tc with the thickness or with the thickness, so what we do is that we plot the variation of Tc with the square of the resistance, and what we see, so basically understanding whether the disorder is having any role to play in the variation of Tc. Yes, it does, because if we just use the Finkelstein model, which accounts for the interplay of disorder and electron-electron interactions, we see a very good fitting with respect to the Finkelstein model of our data with these stoichiometric systems. But if we look at the off stoichiometric system, we actually don't see any fit at all. So, this is no fit. So, we say that in these off stoichiometric systems, the Finkelstein model fails to explain the variation of Tc. Further on, we of course looked at the phase diagrams by doing the magnetoresistance measurements, and then of course as we reduce the film thickness in both the series. So, this is for the niobium 3 tin and this is for the niobium 2.5 tin. What we notice is of course that the anisotropy between the parallel and the perpendicular. So, we measure the magnetoresistance for both the parallel and perpendicular orientation, and we try to look at the critical fields. Needless to say, this was not surprising that this anisotropy increases as you go to lower thicknesses. However, again the same thing, that this is happening at a much higher thickness for this niobium 2.5 tin systems. Okay. So, if we have to look at some kind of so what we want to explain the superconductor insulator transitions which we have observed in these films, and therefore we need to know whether there is any role of superconducting fluctuations. For that we need to measure. So, what we do in the lab is to measure the superfluid stiffness, which is the energy scale to twist the superconducting phase, and we use the low frequency mutual inductance setup to do this. So, we measure the mutual inductance as a function of temperature, and we sort of model this system and solve the London's and Maxwell's equation to get the superfluid density of the system, which can be translated to measure the superfluid stiffness. So, if you look at what the stiffness looks like, so this is for the niobium tin. So, this is the stiffness as a function of temperature. This is for the 32 nanometer and this is for the 8 nanometer, and the similar result for the niobium 2.5 tin. So, what is important to note here is that for both the systems, as you reduce the film thickness, the superfluid stiffness decreases drastically. Well, this is not surprising. So, since our films are becoming more disordered, so therefore, you are getting an increase in the phase fluctuations, the stiffness is decreasing. However, what we notice is that, for films of about 23 nanometer, quite thick films, the stiffness has reduced substantially, okay, much, it's almost comparable to what our 8 nanometer films in this series is showing. So we conclude that these niobium 2.5 tin films are inherently more disordered and inhomogeneous with weaker phase coherence even at extremely higher thickness. And therefore, we pose this question that whether these films can show some kind of a quantum phase transition. So now I will concentrate only on these niobium 2.5 films, 2.5 tin films. So as I already showed this data that as you decrease the film thickness, you go from this superconductor to this insulating films. What is interesting to note is this does not go as one shot, but you see some kind of a reentrant behavior. So you see this is blown up over here for one of the films, for the 12 nanometer film. So this was the microstructure, very granular in nature, small grains separated by intergranular boundaries, and you see this, this and this. So basically you see two drops. So how do we understand this reentrant behavior? So what we first point as the onset, where the resistance starts decreasing for the first time, we christen them as T on local. And what does that mean? We mean that our grains which are still so our grains are just becoming superconducting at this temperature T onset. Then it starts decreasing, so it goes. But here the grains are still small, and if the grains are small, you will have a charging energy. So it will start dominating, and you will start increasing the resistance. However, at this temperature which I label as T on global, you will have the Josephson coupling energy, which is sort of coupling my grains, winning over, the energy scale winning over, and you then start seeing this drop. So basically this competition between the charging energy and the Josephson energy is being able to explain this double behavior or double reentrant behavior of superconductivity observed in this system only, these kind of films only. Well, we are not the first to show this. Okay, people have observed this kind of a reentrant behavior in similar granular bismuth systems and granular titanium nitride systems, but this kind of a reentrant behavior is observed, and the reason being the granularity of your system. Okay. So now what we do is that we want to look at the magnetic field tuned quantum phase transition. So we first take this 13 nanometer film and we look at, we try to measure the temperature dependence of the resistance as a function of different magnetic fields in the parallel orientation. So this, of course, there is nothing much happening. As you increase the magnetic field, you just start getting this pair breaking effect. So you have some effect over here. If you look at the isotherms over here, the magnet resistance isotherms, you do not see much over here. Now we go to the perpendicular orientation. The same film we measure in the perpendicular orientation. We look at this magnetic field, we tune the magnetic field, and what we notice is that for these films you start seeing this magnetic field tuned superconductor to insulator transition. So this is the different magnetic fields we are doing. Looking at the magnetoresistance isotherms, this is exactly what I had showed you before, is the multiple crossing points happening for different temperatures. So we see that, so we can say that this 13 nanometer film is showing some of the characteristics which is similar to the quantum Griffiths phase which we have explained just before. However, we cannot rest here just by this experimental thing. So we have to do the finite size scaling analysis to really understand whether we can see the dynamic critical exponent diverging, and so we did the finite scale analysis. So we took isotherms which were very close spaced in temperature and looked at the crossing point. After this, we plotted the scaling plot. So we made the scaling plot and we altered this scaling parameter T such that this all falls on one thing, and then using that we plotted the L and T versus ln T by T0, T0 being the lowest temperature in this group, and fitting this we obtained this Z nu, which was the effective critical exponent. Of course, this we had to do for all the isotherms for different yeah. Okay. So, this is another set of data where you for different temperature scale where you do see this exactly the same thing, and you get the critical exponents for different temperatures. So, when you get these critical exponents for different temperature, we plot this effective dynamic critical exponent Z nu as a function of the magnetic field, and we see this divergence, which is what we have shown you, which is the characteristic feature of the activated scaling prevalent for this quantum Griffith space. So, however, when we plot this magnetic field versus temperature taking this data, we see something interesting. So, for the systems which have been studied previously, what I had shown you, that as you reduce the temperature, you start seeing an increase in this critical field, and at very low temperatures it almost diverges. But in our case, we see a non-monotonic kind of a behavior. So, we are seeing a behavior which is different from what is seen in a normal QGS, and this is what we see in a normal QGS. So, this is the crossing points. From the crossing points, if you plot the BC versus T diagram, you see that it shows a monotonic increase or a monotonic flattening. Most of the QGS which has been studied is what people have observed. So, we are basically seeing anomalous quantum Griffith singularity in our films. So, to more corroborate this, what we did is that we did more experiments. We did it with increasing granularity. So, we reduced the film thickness. I have already told you before that as you reduce the film thickness, you make the systems more granular, our intergranular regions increase, and this is the result which I am showing you for a 12 nanometer film. Remember, previously I was showing that for a 13 nanometer film, for the parallel orientation, magnetic field orientation, we were not observing any kind of a magnetic field driven phase transition, but in the parallel orientation we do see this. Now, again the same scaling analysis give this anomalous behavior very clearly, this non-monotonic behavior of the variation of the magnetic field with temperature, and you see this divergence of the critical exponent. Further on, if you go, so basically you see QGS seen in both the field orientations. Now, if you go to even lower thicknesses, you see that this transition is driven at the quantum critical point is shifted to extremely low fields. So, it was 4.68 Tesla. Of course, this is for the parallel orientation. For the previous one, for the perpendicular orientation, we got around 2.4 Tesla. Here, this has reduced to around 13.7 millitesla. So, applying a very little magnetic field is bringing us closer to the quantum critical point. So, this is what we see. So, then when we were actually wondering about our anomalous behavior, we saw this paper which had appeared, and this was also repeating an anomalous quantum Griffith singularity in ultra thin crystalline lead films. Their behavior, so if I highlight, so they also saw a magnetic field tuned superconductor insulator transition, they saw the multiple crossing points, and they saw this divergence of the critical exponent, and they also saw this non-monotonic variation of the critical field. And the reason for the anomalous behavior which is given in this paper is attributed to the increased superconducting fluctuations and the high spin orbit coupling which is there in this system. Of course, when we try to reason our things, we have already shown you our measurements of the superfluid stiffness. We have already told you that in our system, of course, there is a large this increase in the superconducting fluctuations which is seen by this superfluid stiffness, by the direct measurement of the superfluid stiffness, which gives us the idea that yes, superconducting fluctuations are quite high in our systems, and probably that is the reason why we are getting this this kind of a anomalous quantum Griffith space in our system. However, in niobium tin, the spin orbit coupling is moderate, so I do not think so that is playing a substantial role. But this is something which is very nascent. I think this is still, people have not observed it a lot, and there is not a lot of studies on understanding this anomalous quantum Griffith space. So, this is the result which we have got. Okay. So, continuing in the quantum phase transition, so we are also working on nanoporous niobium nitride thin films. So, we have made these films which are of course nanoporous. You see the films which are only grown on the around the holes of this nanoporous template. And we also observe the superconductor insulator transition. We have been able to tune disorder in these kind of films, and we see an intermediate metallic state in this. And more interestingly, when we look at the insulating phase of this, we see some kind of a quantum coherence behavior. So, this is basically will be spoken by Amar Verma. So, he has a talk on this thing, and so I will not spend much time on this. So, finally, I will conclude. So, what I showed you that by tuning the disordered morphology through stoichiometry in these niobium nanocrystalline thin films, we are able to show a disorder induced quantum phase transition, and the finite size scaling analysis shows that the presence of the quantum Griffith space, and the divergence which with the decreasing field signals an anomalous phase boundary. You can see the phase boundary over here, and we see that this is actually being this hosting of this phase is driven by disorder and granularity. Finally, I would like to acknowledge, so this is my group. So, Mahesh, this is the work which has been done completely by Mahesh. So, as I said, someone also said that I have just shown the results. So, he has done all the work over here. Amar will be talking about these nanoporous films over here. Ekta is doing a lot of work on vortex dynamics in iron selenide. She also has a poster here, so all three are here. So, I would like to thank my funding agencies and thank you for your attention.
Okay, let's thank Sangeeta for a very nice talk. Questions?
When one does a BCS fit to the superfluid response, it is disordered average. Do you take into account the disorder as well, or
so not in the BCS fit? The BCS fit is a BCS fit. So,
but should it be?
And then we start seeing the deviation from the BCS behavior.
At least in the data that we have shown, the deviation is only of the BKT.
So we see BKT only.
But there should be some effect of disorder also.
But we don't incorporate that when we do the fitting. Yeah.
And it still fits the experiment.
So actually, some of your data in the superconducting state also you have this non-monotonicity, right? So that basically tells you already that there are pairs. Sorry, but I mean in the insulating state you have still this non-monotonicity, right? Like it's on and then.
That is in the superconducting phase.
But some of the data, even like in the insulating, also overall there is some. Right?
So we always have these grains, na? So this grain, our thing is that the grains are becoming superconducting, and then you have the Josephson coupling between the grains, which is creating this global phase coherence. So that is what.
So that regime of like this charging energy, and there even in the insulating regime.
Yes, but then again beyond this, beyond the granular thing, you have this rare ordered formation. So these are much larger clusters. So they are cluster formation. So in addition to this granular nature is what is happening.
Any further question? Okay, if not, let's thank Sangeeta for again a very nice talk. I will move on to